Hi everyone and welcome to this new video about maximum power transfer in AC circuits. This is our example number 2. In this example we will look at a different circuit compared to the example number 1. In this case we have a load CL which is modeled by a series RL circuit and it's connected to a voltage source which has its own output impedance Z of S but modeled by a parallel connection or RCs. So we have a parallel LC circuit for the modeling of the output impedance of the voltage source. The components for the output impedance of the source are the following. So we have the 2 kilo ohms for the RS, and for the capacitor C of C is equal to 250 nanofarads. The voltage source is also given, the value of this, and the question in place is the following. Calculate the values of R and L, so these are the component values of the load, to transfer the maximum power to the load. Now, you know already from the previous videos and the discussion that for maximum power transfer, require, let me write it down, the source impedance must be equal to the complex conjugate of the load impedance. So what is actually our source impedance? The source impedance is a little bit difficult compared to example number 1. There's a parallel combination of the RS and the reactance of the capacitor C of S. So this is the expression. If you now write this in a different form, you will get the following: RS times X of CS divided by RS minus JX of CS. Okay, now if you continue with the analysis for this, you will have to equate the expression of this one to the complex conjugate of the load. So what is the load? Let's write it down also. The load is equal to R plus J of the X of L. So if you have the complex conjugate of this, so that will mean the R minus J X of L. That's actually the expression. So I will need this expression and equate this to the expression without I will get after substituting the values and rewriting this and simplifying the expression. So let's do that first. So I have to simplify the expression for ZS. First I will calculate the reactance of the capacitor CS. So that will be using the value of CS and also the omega which is given. So that will be the following: 1 over 800, which is given in the expression for the voltage, times the 250 nano. So 250 times 10 to the power minus 9, and I will get 5 kilo ohms or 5000 ohms. Okay, that's actually the expression for the reactance of the capacitor. So I will have the following. This is a minus J times R of S was 2000, so 2 times 10 to the power 3 times X of S will be 5000 divided by 2000 minus J times 5000. Yeah, if you rewrite this and rearrange the values such that you have an expression in the rectangular form, you will have the following. After following these steps, you will get 1724 minus J 690 ohms. Now, as you can see, I have to equate this expression to this expression. So this expression has to equate, we have to equate it to this expression because this is also in ohms, of course. So what we have is the following then: 1724 minus J 609 must be equal to R minus J X of L. Now this will result in R is 1724 because I have to equate the real part of the left side and the real part of the right side, and equate the imaginary part of the left side and also the imaginary part of the right side. So I have this. Now the following is X of L. X of L will be equal to 690 That's actually the situation in this case. Now, the last part is actually calculation of the inductance L. For the XL, I know that omega times L, so I will have to rewrite this such that I have the value of the L, so it will be X of L divided by the omega, which is 690 divided by the 800 radians per second, which is already given, and it will result in 0.863 henries, and if you write that in different form, 863 millihenries, and that's actually the required value for the inductance. Using this value for the inductance and this value for the resistor in this load model, you will have the maximum power transfer from the voltage supply Vs to the load. Now, of course, if you again change the values, then you will not have the optimum value. So making this larger or smaller, or making the inductance larger or smaller, will have not the optimum power transfer. This is actually for example number 2. As you can see, it is a little bit difficult compared to example number 1 because the combination here is not series. So if it is series, it's really straightforward, but it's the parallel, then you'll have to do more work by rearranging this expression and using complex conjugate rules. I have dealt this in the other video, so I have not made this in detail in this video, so you can look at other videos about the phases and complex numbers. I will advise you to do that, and you will come to this expression in rectangular form. So this is mandatory if you have to compare the source impedance to the load impedance in complex conjugate form. Then it is advised to represent your source impedance in rectangular form and also your load impedance in a rectangular form, because then you can compare the left and right side for the imaginary and real parts, and then you can find easily your unknowns. That's actually for example number 2. We will continue to clarify the situation also for other subjects, so keep in touch and don't forget to share the video and to like. And I'll see you next time, and have a nice day.